Hey, come on in. What's up? Yeah, we're gonna map. We actually are. It should be fun. Some of you will get to go outside, depending on what you draw. It'll be fun. It will be fun because it's nice weather. It's not too hot, wet. Hmm. How was your week, Orion? Yeah, did you do anything fun?
Yeah, we went on vacation.
Really? Where'd you go?
Utah.
You went to Utah over the weekend, or?
We left on Wednesday and came back yesterday.
All right, that's cool. Were you there for relatives or just for fun?
There for our wedding,
Oh,
and we went there to surprise our grandma for her birthday.
oh, that must have been awesome. Was she really surprised? Oh, that's so cool. I bet she was thrilled. I bet she was thrilled. That's awesome. Who was the wedding? Family member?
But the bride's name is Ella.
Okay.
She's like Ella.
Yeah, is she like a cousin or?
She's not from our family, but
Oh, okay.
so
Now she's family. Okay. Very cool. And it was fun. We had a good time. A candy bar. Sweet. What kind of stuff do they have? All right. All right. That's good. Do they have cake too? Or just candy bar?
Yeah, that's
They had ice cream. That's fun. Where was the wedding? Was it like what kind of a place?
the hall.
Okay. Hey. The Oz. That sounds like fun. Yeah. That sounds very cool. Well, awesome. I'm glad you had a good weekend. Did something fun. Good morning, guys. How are you?
Good.
Good. Did you do anything fun this weekend?
We just woke up.
Oh, you just woke up now. Yeah, I feel ya. Well, Ryan went to Utah, he was saying. Are you? Yeah.
I basically sleep 3 hours past.
Oh my goodness, you were tired. Were you busy yesterday?
And well, obviously, when I actually went to it, I think we get 10 a.m.
Oh man, you were leaving.
I want to wake up at 10 a.m. But I saw so I wake up like.
Oh my goodness. Yep. Yep, that's not fun. That's not a ton of fun. I hate waking up in the middle of the night when I'm supposed to be sleeping and then you can't get back to sleep. That makes me crazy. I just want to sleep. Ah, man. I do love sleeping. Yes, Ian. Just squeak and choose. All right, here comes Megan.
My backpack and put on Sunday school things again.
Oh yeah? No.
Wait, do I have a pencil?
You actually have a pencil right here because you left your lab left. So notice that some of your answers when you were writing. Can you read this? What's that say? You can't read that. That's a scribble. Yeah. So you're going to want to be very careful at how when you write your answers on your labs. This one isn't graded, right? But some of them you're going to hand it to me with a grade. So you're going to want to be sure that you're writing out so that so it's neatly enough so that somebody else can read it. Be sure that you're writing good, full answers. There's your pencil, so you don't lose it. How about you, Maven? Did you do anything this weekend that was fun?
And we played with their friends.
Okay, cool.
Oh, I
Well, Ryan left the state, which is pretty.
All I did at Sunday school was to play soccer.
Soccer. Okay, that's fun. You went to Utah. All right. That's
By
cool.
the way, I was on my favorite side team, and
Okay.
I kept blocking the ball to our goal.
All
I
right.
wasn't the goalie. I wasn't the goalie. I just keep kicking the ball that comes out, into the floor.
Do you play soccer usually, or was it just like one day thing? Like, are you on a team or anything?
I barely play soccer. I barely play soccer because the soccer is what the big boys do.
Oh, okay. All right.
They don't really respect me because I'm
And you said you swim? Yeah. Do you do a sport or anything? Oh, bless your Western.
I went to there. I like Western better.
Yeah.
Yesterday. Where'd you go? Taekwondo. Oh,
Okay, there you go. How about you, Yassine? You do anything fun?
cool.
No. No. It just says very flatly, no. All right. So we're gonna get our lesson started. I got my jar replaced since last week's one was a mess. It doesn't want to open. There it goes. All right, so it doesn't want to stay. I got it. All right, first things first, before we get started in our whole lesson, we want to review for a minute. Why is it important to raise your hand and wait your turn? So for how many of you is this the first time you've ever done a class with other kids? Y'all have done some classes with other kids before? Yeah, this is the first one for you?
No.
Oh, you have done some with kids before. Okay, good. All right, so what are some reasons why it's important? Yeah, so here's why it's important. It shows respect for your teacher and your classmates. If somebody's trying to talk or make a point and you just start speaking out, it can be difficult for everybody to pay attention, and it doesn't show a lot of respect to interrupt, right? So we try not to interrupt. We want everybody to have a chance to talk. And if one person talks the whole time, then not everybody gets a chance to talk. And we don't want people to talk over each other. Do you know what that means? Two people talking at the same time, then you can't hear what everybody's saying, right? Everybody needs a chance to talk. And we want to keep ourselves organized and calm. We don't want to get overly loud and crazy. And we want me to be able to hear and understand, because if somebody has a question, I want to be sure that I address the question, and I can't do it if somebody's chit-chatting or interjecting when they're not waiting their turn. And it's just good manners, right? We want to have manners, and it helps everybody learn better if we listen carefully. So if you have a question, you just raise your hand. If you have something to say, just wave at me. Sometimes I'll say, everybody, just say it, shout it out, whatever.
Mr. Proface.
That's the next thing we're going to talk about. It's getting up and moving around. I'm going to wait for her to come back. Yusra, we're waiting for you. Come on back.
I don't know where's the garbage can.
Don't worry about it. Just put it on the table. It doesn't need to go in the garbage can right now. There you go. We can do it later. That's fine. All right. So be sure that you wait for everyone to have a turn. Okay. This is about staying on task. So this is like a great example is what just happened. Like you saw trash and you were like, oh my goodness, there's trash on the floor. I need to clean up the trash. Because that's what you do when you see trash. But it's all about just kind of waiting till it's the right time. So always be listening carefully. Pay attention to the work you're supposed to be doing. Follow directions the first time is especially important in lab, right? Here we go. Stay in your seat unless you have a good reason to move. If you need to go to the bathroom, get up and go to the bathroom. But trash on the floor, that can wait, right? Until after class. We can just pick it up when we're done talking. It doesn't need to be picked up immediately. Unless it's like food or something that's like spilling, a drink that's spilling everywhere. We can.
No one brings food.
Right, but remember, yes, they do actually. The older kids eat during class. So, yep, you can raise your hand if you have something to say. So put things away that distract you. If you've got a toy that's distracting you, put it away. Finish one task before starting another. That makes sense, especially in lab. Ask for help if you don't understand something. Use your time wisely. How long is this class? The
45 hours.
45 minutes. Okay, and then we go to lab for an hour. We have 45 minutes to cover the entire lesson. If we get off task and we're not covering what we're covering, class is going to be over and you're going to be left to cover it by yourself without me, which means when it comes time for your test, you won't have gotten any input from me. You'll have to do it on your own. Who wants to do that? Who would
No one.
who would prefer? Yes, no one. Who would prefer to cover it as a group the way it's meant to be covered? Everyone agree? Everyone agree. All right. So remember, focus on your learning, avoid distractions. Let's get our work done. That's what we're here for 45 minutes. All right, are we ready? Okay, now we start our lesson. Do you have a question? Your hands up. You're just stretching.
Yeah.
What's your question?
I just said yeah.
Oh, you just said yeah. Okay. All right. So we're going to talk about exploring Earth's surface today. And we're going to be talking about mapping during lab. We're going to actually make maps during lab today. We're going to map different parts of the house and the yard and the deck. Should be kind of fun.
So we're going to go.
Whoop, wait. Did you have a question? Hand? Some groups will be going on the deck. Right. All right. Topography. What does topography mean? Who knows? Does anybody know what topography is? You know?
The scientist that's studying to make maps.
Kind of. Those are cartographers. You're real close. Topography is the shape of the earth. That's what a topographic map looks like. And it tells you how high something is, how low something is. It's about mountains and valleys and things like that. Sorry. Wait. Question? Yes.
But everything's flat.
On that map? Actually, I'm going to show you in a minute how that map works. It's actually showing you where the hills and valleys are. All right. Landform. A feature of topography. This one is something that is flat, low relief. What landform is flat and low? Does anybody know the name of it?
Ground.
Wait, hand. What is it?
Plain.
Plain, hand. Yes, plain. Very good. We're talking about a plain. Low and flat is a plain.
Wait.
Sometimes this is where you'll find farms. Yes.
Wait. So when you said the word plain, you meant the plain?
I meant plain like that. Low and flat land. There's different kinds of plain. There's plain, PLAIN like this. That means boring. You know, it's kind of plain and simple, boring. Then there's PLANE, which can be a jet plane, but it can also be like a board or a floor. Those are planes as well. All right. So this is a landform that has a high elevation, but a level surface. Do you know? Plateau. Very good. There's also another word for it. Does anybody know the other word for a plateau? Sometimes you'll hear it in the states that have a lot of Spanish speakers. Do you know? Yeah, it is a feature of topography, but there's another word for it. Do you know? What now? Amor? No, we're close. Maven, do you know the word for table? Mesa. Very good. You heard of Mesa, Arizona? That's table in Spanish. Do you see how that looks like a table? All right. So sometimes you'll hear that referred to as a mesa, but it is a plateau. Very good. All right. This one is where you have high elevation, high relief. What is it, Maven?
Mountain.
That's a mountain. Do we have mountains in this state? Everybody, yes or no?
Yeah.
Yes. What mountains do we have? Does anybody know what range it is? You know?
I have the mountains around my brother's window.
Out the window? Okay.
Yeah.
Okay. So we are at the very bottom of the Appalachian Mountain Range, at the very southern end of it, right? Okay. Now we're going to talk about what is elevation. Elevation, we are measuring the height of something above what? Do you know above what?
About the temperature.
No, not temperature. Good guess.
High
Do you know?
level?
Sea level, above sea level. This is the height above sea level. So if you have your binder and you did your work, you should be able to look through and see a lot of these. Are you seeing your answers as you go through? See how that works? So for those of you who don't have your binders out, this might be a way to get the right answer as we go along. So we measure above sea level. Why would we do that? What's special about sea level? What?
Because water is always.
Yeah, water's always even. Why is water even? What do we think? Where do all the rivers and all of the streams end up?
The sea.
Yeah, they end up in the lowest possible place. And
And also, they have
the what?
they heat up and then go to the clouds and then.
Yeah, that's water cycle. Yeah, so the water runs downhill to the sea. Sea is the lowest point. So we measure from sea level because that's the lowest point. Okay. And what does a relief mean? When you keep seeing the word relief, it means, wait, don't interrupt. Relief is the difference in elevation between landforms. So there is a relief between the top of this hill and the Chattahoochee River down there, right? There is a difference in the elevation of the landform we're on and the river down there. Which is going to be higher, the river or us? You don't even have to look to know. What is it?
The river.
Us. Yeah, why? Because if the river were higher, the water would do what? It would go running out, right? So the water is at the bottom of the hill, right? We're at the top of the hill. All right, so let's look at this. When you see it, this is a chart. Remember we talked about charts and graphs and things like that. This is a chart that's showing that things are inside of other things. So this thing at the bottom in the dark purple is inside the thing in the medium purple is inside the thing in the light purple. Do we see how that works? They fit inside of each other like kind of like cups that would stack. So the Bitterroot Mountains are a part of a mountain range. Okay, so we're going to call it a mountain range. See the little circle on the top map up there? That's kind of where you were, isn't it? Yeah, not too far from where you were this weekend. All right, so that is the Bitterroot Mountain Range. But the Rocky Mountains are a part of a mountain system. So the Bitterroot Mountains are a part of the Rocky Mountain Range. And the Rocky Mountain Range is part of a mountain system. And that is part of a mountain belt that stretches down the western sides of North and South America. So you see you have a mountain range, a mountain system, a mountain system, right? And then a mountain belt. Yes, ma'am.
Does your dog ever come out during class?
No, not typically. But that's a good example of that's not on task. We need to talk about this is what we're talking about right now. But we can ask. Oh, he wouldn't like that at all. Yeah, but he does. Yeah, yeah, but he doesn't like that. He likes his quiet when he's here by himself. But no, you could ask. That's the kind of thing that you ask like when class is over or when we're wrapping up, right? All right. So next, the American Great Plains is a large area of land with mainly one type of topography. And it's an example of what? What do we think? It's going to be an example of a landform region. And in this case, it's what kind of landform? We just talked about it. It's not a mountain. It's not a plateau. It's a plain. Good, everybody. Yes, ma'am. Oh, are you going to answer that? Yep, there you go. All right, so now let's talk about longitude and latitude. All right, can I trust to give you each one of these blow-up globes that you're going to hang on to it and not toss it around?
Sure.
Okay, so you're going to hang on to it and not toss it around. All right, here's yours.
Are you
Yes, they are. That way I can get lots of them because buying actual big globes for everybody would be expensive, right? So, for you. Here's for you. Okay, now you can look at it up close on your globe as we talk about stuff. All right, so we have latitudes, lines of latitude. They're also known as parallels. See the way the lines of latitude run around the earth in circles like that? You see them?
Mm-hmm.
All right, see why they're called parallels? What does parallel mean?
Like they won't ever.
Right, two lines that run like this next to each other and never intersect. If one is tilted, eventually they're going to intersect, but they never intersect, right? All right, so they're parallels, and they run east to west. Do we see that they run east to west? Right, east to west, and they measure the distance from north to south. So if you look, they're running here east to west or west to east, but they're measuring the distance going from north to south. And they're measuring it in degrees is what we call it. All right. So if you look carefully, you can probably find your equator somewhere on your globe. Yeah, there's going to be lots of them, honey. They're out there all day. So if you look on your globe here, you can find somewhere there will be a line Here we go, right in the middle of the Pacific Ocean, you're gonna find your international date line. It runs this way. This blue line is your equator. Does everybody see the equator? All right, if you look on either side, you see how these parallels run this way? And see it says 10, 20, 30. Does everybody see that? Okay, good. Now you know what we're looking at. All right, they're parallel to one another. They never meet. They cross the prime meridian at right angles. We'll talk about the prime meridian in a minute. And they lie in planes that cross the Earth's axis at right angles. What does that mean? That means Earth's axis, yep, so you're not going to toss around. So Earth's axis would be like if you were to drive a pole right through here and then out the bottom, right? Yeah, well, it would. But we'll pretend it's not a plot. But if you were to drive a pole all the way through, they're going to be a right angle as this line comes to the pole. Right angle is like this, right? So the corner of a square, not like that, not like that, like that. With the letter L. See how that would work? All right, and they get shorter towards the poles. Why are they getting shorter towards the poles? Yes, it's a sphere. So they're getting shorter as they get, the circles are getting smaller, the biggest ones at the equator, and then they get smaller and smaller and smaller and smaller, right? Smaller, smaller, smaller. And the equator is the longest with the great, it's a big old great circle, right? These are what you call horizontal. If you're looking at a globe, the way we typically look at a globe. The reason that's in quotes is because we orient globes that way, North Pole, South Pole, up, down, left, right. But in space, that's not really how it is, right? In space, it's different. But as far as how we map, yes, as far as we map things, we think left. We tend to think that, you know, if you look at a map, the right is east, the left is west, up is north, down is south, right? So these run horizontally this way, not this way. Yes, ma'am.
I already know about space because I'm up there.
Good. We're going to learn a whole lot more about it this year, too. So what degree is at the equator? Who can tell me? There should be a number next to it. Who sees a number? Right in the middle of the Pacific Ocean where those lines are.
Yeah.
Yeah, but what's the line at the equator?
It's
20.
17.
20. Look at the blue line. And look at the lines that, so you're not looking at those. Those are longitude. You're looking at latitude. Okay. Right here. 10. There's two numbers there. Do you see there's two numbers in that spot? 0. Okay, very good. Now, if you look at that, which one do you think is for the equator? Look at the latitude lines on here, above and below it. And what are they? Almost. So if you've got 10 degrees above the equator and 10 degrees below the equator, then the equator is going to be what, everybody? 0. The equator is 0. The poles are going to be what? What's at the pole? Does anybody know? The poles are going to be 90. Okay. Now, when you get into geometry, you'll learn that, like, you know, half a circle, a line is 180 degrees, a circle is 360 degrees. Half of 180 is 90. So we have 180 of these lines, right? Because it goes from 0 to 90 and then 0 to 90. So we have 180 of these latitude lines. And a degree is roughly 111 kilometers. All right, now you've found the latitude. Let's look at the longitude. All right, so we don't call these parallels, we call these meridians. All right, and they run in a north-south direction, not east-west, right? North-south. And they measure distance east or west of the prime meridian. Who can you find the prime meridian? So look where it is up here and see if you can find it on your globe.
Is it on the Atlantic Ocean?
Look at it right here. It's the red line.
It's on the Atlantic Ocean?
No, it's not. It's east of the Atlantic Ocean. It goes through Europe, Africa. You found it? You found it? Okay, this is interesting. The prime meridian is where it is because of war and conquest. War and conquest. Yeah.
In the sea.
Can you see what's there's? I don't think you can see it on yours. It runs through a city. If you look at, hold on, not that one. Prime meridian is going to be right here where it says 0. It runs through a city in, I don't know if they put it on there. It's not very clear on your globe. It runs through a city called Greenwich in England because Britain was a huge empire and they owned most of the planet when people started deciding to basically solidify how we're going to call things. When we started coming up with how we're going to name things, how we're going to do, what is the official scientific way we're going to map the world, Britain happened to own most of it. So they said, we're going to let this prime meridian run right through us because we own everything and we get to choose because we own everything and we have the power. So that's why it ended up there. Yes, ma'am.
Banana lasagna actually exists.
Okay, that's off topic. We need to be on topic, okay? So cross the equator at right angles. Do you see how it crosses the equator at a right angle? Like that, right? There it is again. And they are halves of circles because if you were to trace all the way around the globe, it would be a full circle, right? Like if you were to go all the way around it, but it only goes from pole to pole, and that would make it half of a great circle, right? They are vertical in quotes, because again, this is just how we hold our globe. They are vertical as opposed to the latitudes being horizontal, right? The prime meridian is how many degrees? Anybody see what it says? 0 again, all right? Don't toss the ball. All meridians converge. Where do they all come together? Look at those lines, those vertical lines. Where do they all come together?
The North Pole.
North Pole and
South.
South Pole. Very good. North and South Pole. All right. At the poles, and they are semicircles or ellipses, and 1 degree varies from 110 kilometers to 0 kilometers. Why does that distance vary? Remember, the other ones, our latitudes were 110 kilometers roughly. Question? What? Sorry? That is the pole. That is the South Pole. Okay, so why? Yeah, that is the North Pole. Okay, so why would they be different? If our latitudes were all roughly 110 kilometers apart, why would our longitudes vary in distance? Where are they 110 kilometers apart? Where do you think?
In the middle.
What do you think?
In the middle.
In the middle, at what? What do we call that big line around the middle? At the equator. Good. They are 110 kilometers at the equator. And when are they 0 kilometers apart? Yes. No. At the poles. See how, if you look at the shape of them, they're like this in the middle, and as they go towards the top, they kind of squeeze together. And as they go towards the bottom, they kind of squeeze together. Yeah, because of the shape.
Yeah, and
Yes.
There's a mistake.
Oh, where?
It says 111 kilometers.
Oh, that's correct. I'm saying 110 because that's the number in my head, but 111 is correct. I'm wrong. All right. So here's your trick for how to remember the distance between latitude and longitude. Longitude, remember the long parts or the poles of a ladder that run up and down, think north-south. Latitude, remember the short rungs. The short rungs that turn those 2 long parts into a ladder and act like steps. Those go east-west. Longitude, latitude, like a ladder, right? Long poles, ladder steps. That's how you remember longitude, latitude. Real easy. And that's the little guy that says, remember, remember. Okay. We also have an international date line. This is important because this is how we know what day it is. Okay. Wait. So this is imaginary. It's not a real line, right? Nobody went and drew it, right? So it's imaginary. The international date line is imaginary north-south line that runs through the middle, don't toss, of the Pacific Ocean about halfway around the world, close to 180 degrees of longitude from the prime meridian. So that means it's the opposite side of the globe from the prime meridian. So if you remember where you saw your prime meridian that ran through England, remember? Spin your globe around and look at the exact opposite side, and you're going to find the internet. Did you find it, Orion? Okay, your international date line. And again, that cuts through Greenwich, the prime meridian. It has no force of international law. It's there for convenience, right? And any given day has to start somewhere. We have to decide when Tuesday started, right? I mean, just for the sake of calendars and business and life, we have to know when Tuesday started, right? Yeah, that looks like it. It's not recognized as a legal entity. It has no international status and was not defined at the 1884 Prime Meridian Conference in Washington or by any other treaty, according to the website of the Royal Observatory, which is in Greenwich, which holds the Prime Meridian. You can go and you can stand on the Prime Meridian. They have it like on the floor. It's actually there. Like you can see it in that little space. It's like a museum, right? It zigzags. It zigzags quite a bit. Why would it do that? One of the biggest zigs occurs around Kiribati, an island nation of 32 atolls, little tiny islands, right, that straddle the equator. In 1995, Kiribati moved a chunk of the line to the east so that the entire country was on the same side. Imagine for a second that this imaginary line that we've decided says when Tuesday starts ran through the middle of your country. And your next door neighbor is in Monday and you're in Tuesday. How'd that work? Would that be easy for business, for school? Can you imagine doing school? When do we wake up? What do we do? What day is it? Right? That's confusing. So they took it and went and moved it around their little island because that made sense. The midway point actually crosses very few bits of land. Most of it is in the water. 3 islands that are part of Fiji are a part of this. So they've moved it around most of the land for the sake of having business that makes sense. So it addresses the phenomenon of gaining or losing a day, which is what Ferdinand Magellan did. So Ferdinand Magellan, who was an explorer, he kept noticing it was a different day when he got to different parts of the world and was kind of confused. So that's how we did it. We decided, okay, here's a line, right? So this lady is going to explain to you how it works on a watermelon.
Literally had the longest day ever. Hello, that's stressed. Maddie, a really long day. Maddie, hello, hello. Sorry, what do you say? Watermelon? No, thank you. I don't want watermelon. I was just saying that I had to get at 3 a.m. to call my boss in LA. No, it's not a bit. I'm sorry, what do you mean? Samara and Tara, basically, a time traveler. Care to explain? Sure. So we've all had days that feel like the longest day ever, but it got me thinking, how could I literally have the longest day ever? What would I have to do? And then that got me onto the very confusing subject of global time zones, the international date line, and time travel. Imagine this watermelon is our planet. It's a rough rotating sphere, and it rotates an entire 360 degrees in 24 hours, which is the time it takes from sunrise to sunrise. Knowing this, we can work out how far the world travels in 1 hour. So if we take our 360-degree rotation and divide it by 24, we get 15. So every single hour, the world rotates 15 degrees. And we mark this using vertical lines of longitude, also known as meridians. And quite handily, this watermelon here has gained to represent those quite nicely. 24 vertical meridians, each one marking 15 degrees and 1 hour's worth of time. It's all very well having 24 1-hour zones on our planet, but we need them to start somewhere. And this is where the Greenwich Meridian comes in. It marks 0 degrees, the point where time starts, and it runs through Greenwich, London. The Greenwich Meridian, marked out by my beautiful red sticky dots, was chosen as the starting point of time of 0 degrees because at the time in 1884, 72% of the world's commerce depended on sea cards, which used Greenwich as their prime meridian. So this is where it begins. It's midday GMT, Greenwich Meridian time. The sun is directly overhead. However, it was midday 1 hour previously, plus 1, that's to the east of our line. So if I just rotate the Earth backwards 15 degrees, you can see here we find midday on +1. I then rotate to the east 15 degrees and continue to our -1 line, we find it's not midday till 1 hour later. And this is why we have plus lines of longitude and minus lines of longitude as the Earth continues to rotate in an easterly direction. As long as we know the location of 2 places on Earth, we can work out the exact time difference between them. LA is 120 degrees away from the UK. I divide 120 by 15, that's 15 degrees per hour, against 8. That's 8 hours. So the UK is 8 hours ahead of LA, -1, 2, 3, 4, 5, 6, 7, 8. Now, the stress value called at 3 a.m. will subtract 8 hours. It was only 7 p.m. in LA. The Greenwich Meridian marks time 0 and enables us to add or subtract hours so we can work out time differences across the globe. But we need a way of defining exactly when a new day starts. After all, you can't continue to fly around the world in an easterly direction, just subtracting hours as you go. If you would lose days, and that's time travel, which is impossible. Yet, as there are 24 hours in a day, it makes sense for a day to start 12 hours or 180 degrees away from the meridian line. So if I subtract 12 hours, we find ourselves at the international dateline. Now, here we have from 12 p.m. till 12 midnight on Monday. The moment we cross over, we find ourselves at 1 a.m. on our Tuesday. Tuesday then starts to grow, slowly eating up Monday as the Earth rotates, until eventually we get to Tuesday, 12 p.m. Now, there's only so much I can show you with a watermelon, so I'll get some video with better graphics down the do. So the date immediately to the left-hand side of the international dateline will always be 1 day ahead of the date immediately to the right-hand side of the international dateline. In fact, if you were to go to the North Pole, you could walk around in circles, crossing from day to day. Conveniently, the international dateline largely lies in the Pacific Ocean. However, you can see it's not quite straight, as it's been moved slightly over the years to accommodate the needs of various countries. I'm sure you can imagine it can be pretty frustrating for two countries to do business with each other when they're only a mere few hours apart but exist on completely different days. For example, over here, these guys can be working or be busy on a Monday and only a few hours away, and everyone's still chilling over here on a Sunday. But that is exactly what happens for Tonga and American Samoa. Tonga and Samoa are in the same time zone but are split by the international dateline. That means when it's 5 p.m. on a Monday in Tonga, it's only 5 p.m. on a Sunday in American Samoa. But they're just an hour and a half flight away from each other, a mere 552 miles. Therefore, if I spent my entire Saturday on Tonga, I could then catch a plane at midnight and an hour and a half later find myself in American Samoa at 1:30 a.m. on Saturday and have the whole day again. Technically, my entire day could last 48 hours, and that's just by crossing the international dateline.
So you could have the longest day by crossing the international date line. That's pretty wild, right? All right, so let's talk about types of maps. Yes, ma'am.
Was that you?
No,
Or did you just?
no, it's just a video. No. So we have different types of maps. Let's talk about projections. So we have a cylindrical map that's projected onto a cylinder, latitude and longitude lines. Now look at the latitude and longitude lines on this map. How would you describe them?
A grid.
Yeah, they look like a grid. Very good. That would mean that they are parallel. Your latitude lines are all parallel. I mean, your latitude lines are all parallel, sorry, and your longitude lines in this case are parallel. Remember, they're normally shaped like an ellipse because they're going from pole to pole, but in this case, they're straight. And that's just because we have projected the globe onto a cylinder and drawn it out. And it's just one way of mapping. A flat map will always distort the way things actually look. Like if you look at a flat map, they tend to make Canada and like Russia look really big, and they're big, but they're not that big. But it's because we've stretched them out because they're normally on this part of the curve of the earth, right? So yes, it does. So they're designed to help sailors circumnavigate the globe. All latitude and longitude lines are going to intersect at those 90 degrees. And an example would be like a Mercator map. Then we have conic maps. So these are created by setting a cone over a globe and projecting light from the center of the globe onto the cone. And they're shaped like this, right? And the distances between regions and areas get distorted at the poles, but they're good for mapping regions that go east to west or west to east, right? So a Lambert conformal conic map is probably a better known type of these. All right, and these are just, the meridians are equally spaced, the parallels represented as circular arcs. See, so in this case, the parallels are circular arcs, the latitude lines. Yes? Is that on topic? Does that have to do with the map? Okay, so we're going to stay on topic. Can you sit up, please? You're kind of in Maven's space. Can you sit up and give Maven a little more space? Thank you. There you go. All right, then we also have projections called, this is a planar map and it's projected onto a plane. Yes.
Top or below?
What do you mean?
Are they closer to the Arctic or the other Arctic?
I don't know what you mean by they. What do you mean by that pronoun? What do you think?
Here
Are
or
we?
here?
Us?
No. Are the people in the video closer?
Oh, she was in England. So she was where we were looking before. So these are projected onto a plane and they show the distances and directions accurately from the center point, but they distort shapes and sizes everywhere else. So the center's accurate, like right here, this North Pole is accurate, but look at how distorted everything else is, right? So these are good for navigators that are trying to find the minimum distance from one point to another. And the circles are like, we got straight lines going in here, coming out from the center, like spokes on a wheel, right? And then you have pseudo cylindrical or oval maps. You ever seen one like this? This one's kind of wild looking, right? Mm-hmm.
That one on the bottom looks like a mom.
Oh, does it? Okay. All right. So they do these. These are much more accurate when it comes to distance and not distorting, but you see you have actual gaps in the map, right? So you have to just kind of ignore the gap and know that if you're crossing from here to here, you're not actually covering any distance, right? It's just the map it's hard to take something that's on a sphere and make it flat so you can view it, right? So these are created by wrapping a cylinder around the globe and then projecting light through it. That's how you get these oval ones too. And let's see. Then we have topographic. Okay, this is the one you mentioned before, Yusra. So topographic maps show changes in elevations with these lines that they call contour lines. And here's how it works, basically. The closer together the lines are, the steeper the land, okay? Each of these lines has a number on it, and it tells you the elevation, all right? So if you look, none of these lines, except where they run off of the page, when they run off of the image, they're actually loops. They're like these irregular loops that go everywhere. So like you put your pencil down and you don't pick it up, right, until you get to where you're going. So the steepest point on this map is actually going to be right along the edge. There's a cliff there. It's very steep. See, there's like a cliff that goes into the water. You know it's a cliff because you see how close the lines are. And then your highest points on the map are going to be where you can see the whole circle. So you can see one down there where there's a little 63. You can see another little circle up there in the middle where it says what, 137. Where those circles are, that's showing that that area all there is the same elevation. So everything below it, the further apart is going to be less steep. So if you wanted to hike to right on top of that little circle up there that's all by itself, you would pick where the lines are farthest apart because that's the least steep path. You wouldn't want to go hiking straight up a very steep part. That would be really crazy. So they never cross. The lines never cross. They're irregular loops. The closer together the lines are, Yusra, don't pull her off task. The closer the lines are, the steeper the land, right? And if you look, it says right here, stream flow. When contour lines cross valleys, they form a V shape. The V shape always points uphill and you can use it to determine which way water will flow. Do we see the little upside down V's right there and right there? You see those? Right here. Whoopsie, right here and here. So this is a steep top of a mountain. And here's where it gets steep and it gets lower. So water would run down here towards the ocean. Contour lines form irregular circles or loops. They don't interact. They are concentric, one inside of another, inside of another, inside of another, right? And the elevation between lines is never higher than the value of the higher contour line. So, for example, between a contour line marking 500 feet and another marking 600 feet, there could not be a point where an elevation is 650. Yusra, there you go. Thank you. All right, let's talk quickly about this stuff. So, geologic maps are going to show distributions of rocks and soils. What is that a map of, everybody? What are we looking at?
Geologic.
Yeah, but what is it? Where is that? That's Georgia. Thank you, Orion. That is Georgia. Okay, and this is showing where you're going to find different kinds of rocks and different kinds of soil in Georgia. Okay, then we have these bathymetric. These are for bodies of water. If you ever go out in a boat on a lake, Yusra, can you come back to your chair so that you don't distract Yassine? Yusra, thank you. So you can see underwater topography. So this is kind of like where we looked at the topographical map where you could see the mountains. This is almost like you take that and you flip it upside down and it goes down deeper and deeper, right? So you can see boats use these so they can see what is like under the surface. How deep is the water here? Yusra, sit up, please. We're in class. Thank you. And it's just like sonar, that kind of thing. And then you have map legends. Okay, map legends are basically like a code to understand the map. So they may have things on them like that's a compass rose. That tells you where north is. This guy right here is a compass rose. And they might tell you, please don't toss your ball. And these might tell you things like, where do you go camping? Or where's the volleyball court? Right? That's where you find these kind of maps. So this is a map right here of Fowler Park in over in Cumming. So if we look, what's the number of the running track? Here's the running track. What number is there? And if you didn't know it was the running track, you could go over here. It says track and field is letter C. There's letter C. I see a number 11 there. How many playgrounds do we have? A playground is noted by this little yellow triangle. Where do we see them? I see 1, 2, all right? Is the dog park nearest the paved walking trail or the greenway? Okay, what's the dog park? It says H. So that's right here. This is the, what? Paved walking trail, because it says it right here. And the greenway is this guy right here, because it says it right there, Big Creek Greenway. So is the dog park near the paved walking trail or the greenway? What? Nope, I'm answering this question. Is it going to be near the greenway or the paved walking trail?
Green.
No, here's the paved walking trail. It's going to be closer to that. Yep. And how would you get to the administrative office from the maintenance facility? Well, you'd have to go, maintenance facility, L. Where's L? Here's L. And how would I get to the admin office? The admin office is M. That's over here. So I would take Caroline Way if it were me, right? Scales. All right, we got to roll through these. Okay, we're going to roll through these. Scales can be given as a graphic scale, which gives you an image, a verbal scale, which gives you words, 1 centimeter equals 1 kilometer, or a representative fraction, which is 1 to 100,000, which means that this is actually 100,000 times smaller than it is in real life. Let me rep through these because we're running short on time. We can do all kinds of remote sensing. We can use satellites. We used to use something called Landsat. We don't use it as much anymore. There was also Topics Poseidon for the ocean. We don't use that one as much anymore. You can see it kind of went out of fashion in 2006. But then we also have sonar beams that boats use, and they can tell the depth of the water. And I'm going to skip the video on GPS. Y'all can watch it on your own if you want, because you can come back and the links will be in the email. But, and then we have combined things like Waze. Anybody's parents use Waze in the car? I use Waze everywhere I go. So this combines a photographic map, so like a picture, right? It combines a road map, right? And then it's GPS integrated. GPS uses 3 different satellites and they position themselves to tell you where you are on the planet. So definitely go back and watch that video. Okay, there'll be time, you'll have time to go over it at home. And then we've got there's all kinds of different mapping things. We don't need to go over all of them. So I'm gonna read this to you real quick. And then I'm going to show you what's going to be on your test so you know what to study because you have a test this week, okay? Yep. First test, so I hope you've been paying attention. All right, so throughout the history of navigation, latitude could be found relatively accurately by using celestial navigation, the stars, right? However, longitude could only be estimated at best. This was because the measurement of longitude is made by comparing the time of day difference between a mariner's or a sailor's starting location and new location. Some of the best clocks in the early 18th century could lose as much as 10 minutes per day. That's a lot, which translated into a computational error of 242 kilometers or 150 miles. In 1764, a British clockmaker named John Harrison invented a seagoing chronometer. We do a lot of Greek and Latin roots in science. If you know, meter means to measure, chrono means time. So a chronometer measures what? Time, right? A time measurer. And it was the most important advance to marine navigation in 3,000 years of open ocean marines that have been going to sea. Don't throw, no, wait, get it after class. And don't throw them, remember? Harrison used British naval officer and explorer Captain James Cook used Harrison's chronometer to circumnavigate the globe. And when he returned, his calculations of longitude based on the chronometer proved to be about within 13 kilometers or 8 miles. From information he gathered on his voyage, Cook completed many detailed charts of the world, completely changed the nature of navigation. By 1884 international agreement, we have our prime meridian located at 0 longitude, passing through Greenwich, right? Okay, these are what's going to be on your test. So what you need to do, there will be a folder. Where do you find the folders with stuff in them that you can look at? Do you remember where it is? So it's in Dropbox. So you go to the website, you go to Dropbox. I'll put this in the weekly email. So you remember, you go to the website, you go to Dropbox, you go in there, and there will be one that says resources. And you go in there and it will say unit tests. And in your unit tests, it will tell you, your unit 1 test. And you'll click on it and it will have this exact image. And these are the topics that will be on your test. So you know what to study. When it's time to take your test, you go to Teacheries, you open up your test, and then the clock starts. You don't have all day. You usually have about an hour. Yeah, it'll tell you. Most tests are an hour, and you need to be able to complete the test. You can't, if you want to walk away from it and come back, that clock is still running. So if you start the test and you're like, oh, I don't feel ready, I'm not ready, it's probably too late. You need to be ready before you start. So you study, be sure you understand all of these topics really well. You can go back and watch last week's class video. This whole slideshow is saved for you. And you should know where to find that too. That's in our YouTube channel, which is also on the website linked. And you can also go back and look through your notes. The actual slideshow without me talking is also in your Dropbox. So you have everything to access. And I'll put that in the weekly email so you remember how to do it. Okay? So if you could collect your globes and bring them up to me, we'll go ahead and get started with lab. Good job, guys.